Okay, today we're going to talk about some different types of methods for integration. So namely some rules involving the inverse trig functions and then also using long and synthetic division to find out how to do some more log integrals. So this will be on top of what we've already learned about use substitution, and some of those skills that we learned when we did use substitution will come in handy here. So integrals to which the log rule can be applied often appear to be in disguised form, and so usually what has to happen is that we have to use either long or synthetic division to basically be able to work the problem. Okay, so what to look for? You're looking for a rational function, so remember rational function just means a fraction, with numerator of degree greater than or equal to that of the denominator. So really you're looking for, in our case, bigger on top. Okay, that's probably a pretty good indication that you're going to use either long or synthetic division, or you could be equal. You don't necessarily have to be greater than, you could also be equal. Okay, so in our first example, we have a rational function. We are equal in our exponents here. So this right here is an x to the second power. This right here is also x to the second power. And so what we notice is that it's a rational function and that the degree of the numerator and denominator are equal. So I'm going to use long division, and the reason I have to use long division is because this is not of the form x minus c. So if you remember from Algebra 2 or Pre-Cal, we can only use synthetic division, which is obviously much faster and easier. We can only use that when we're dividing by x minus c, but since we're dividing by an x squared term, we're going to have to use long division. Okay, so I set up my long division. Here's the picture of my work. I have x squared plus 0x plus 1. So the reason that I have that 0x there is because there is an x term missing from the denominator, so I have to put that in somewhat as a placeholder. And then on the inside here is my numerator. Okay, so I'm just going to do some laser pointing here. So what I do is I take x squared, I divide by x squared. That gives me 1. So I put 1 up here at the top when I do the division. After I divide, I multiply. So 1 times x squared plus 0x plus 1 gives me this line. And then I subtract. So what I don't have there is my subtraction symbol. So I'm subtracting this entire thing. Okay, so when that happens, the x squareds cancel. I get x minus 0x, which is x, and then 1 minus 1, which also cancels out. Okay, so that gives me x as my remainder. So if you'll remember, when we write this after we divide, we take our quotient, which is 1, and then we add the remainder divided by whatever the original denominator was. So x squared plus 1 in this case. Okay, so what that's allowed me to do now is rewrite the problem, the original problem, as a much nicer problem, which you see right here. Okay, so we have the following problem. What I went ahead and did is just split it into two integrals, because this first term is easy to integrate because it's just 1, and so I know that the antiderivative of that is just x, which you see down here in the answer. And then this antiderivative right here, this integral, is going to require a u substitution. Okay, so I let u equal to x squared plus 1. That means that du is equal to 2x dx. And I don't have 2x dx in this integral, I only have x dx. Okay, so I divide by 2 in order to get what I have in the problem. Okay, so that leads me to, and all of that is written right there as well so that you can see that. Okay, then what do we have? We have this integral, 1/2 the integral of u to the minus 1 du. Well, I know that that's the natural log rule since it's u to the minus 1. Okay, you could also think of this as being 1/2 the integral of 1 over u du, or you could think of it as being 1/2 the integral of du over u. Okay, all of those should signify to you that the rule that you need to use is natural log. So our answer, integrate 1, you get x. Integrate 1/2 u to the minus 1, you get 1/2 natural log of u, which was x squared plus 1. And then don't forget your constant of integration. Okay, so this is a similar example, so I'm not going to go to it as in depth as I did in the first one, but you can kind of see the work here. Again, because the degree of the numerator is higher on top, then we're going to use either long or synthetic division to be able to find the integral. So in this case, again, we're going to have to use long division because of what we're dividing by here. We're dividing by x squared plus 2. Okay, so I take x to the fourth, I divide it by x squared. That's how I get the x squared term here. Then I multiply x squared times this entire line here. So let me start doing some laser pointing so you can clearly see what I'm talking about. Okay, so x squared is here. I multiply x squared times x squared minus 0x plus 2, and that leads me to this line right here. Okay, after that I subtract. So what ends up happening there is that the x to the fourth terms cancel out. 0x cubed minus 0x cubed cancels, and then 0 minus 2 is how I get the negative 2x squared. So again, you'll notice that I put in a lot of these placeholders because we have a lot of terms missing in the numerator and denominator. So it's very important that you remember to do that. Okay, once we get to this line right here, this line right here is what I'm talking about. We divide again, so I would do negative 2x squared divided by x squared. So this negative 2x squared divided by this x squared here, that's going to give me negative 2. I'm going to put that above the constant term there so that I have everything lined up. And then I multiply negative 2 times this denominator here. So negative 2 times x squared is negative 2x squared. Negative 2 times negative 0x is 0x. And negative 2 times 2 is negative 4. Okay, you'll see that when I did this, I had a couple of just miswrites or typos, so I kind of corrected over those. So when I end up subtracting this, let me come down back to my pen here. When I end up subtracting this line right here, everything ends up canceling out except for x, and so that's my remainder. So what I'm left over with when I divide is my quotient, which is x squared minus 2, plus my remainder, which is x, over the original denominator, so x squared plus 2. Okay, so now we're here. We have this new problem that's right here. And so basically we now just take the antiderivative. Well, this term right here, the x squared, is easy to integrate. It's just a power rule problem, so we're going to bump up and divide. So that's how I get the 1/3 x cubed in the answer. This term is also very easy, the minus 2x. The antiderivative of that is just negative x squared. And then just like example 1, this term right here has to be integrated using a substitution, and it fits the log rule. So again, if we set u equal to x squared plus 2, that means that du is 2x dx. And solving for x dx gives us the 1/2 du. And so that's where this 1/2 and this du come in. What's left over is u to the minus 1. And so when I integrate that and resubstitute back in for what x was, I get 1/2 natural log of the absolute value of x squared plus x plus c. Okay, example 3. This time we're going to be able to use synthetic division because we're dividing by x minus 2, which is what we talked about earlier, something we're able to use synthetic division for. So again, notice that the numerator is bigger on top. Okay, since this is an x to the first power, in the numerator, we have an x squared term. Okay, so this time I'm able to use synthetic division. So if you just remember some things about synthetic division, the 0 of the denominator goes in this box. So that's where I got the 2 from, is because it said x minus 2 here. The first thing that happens is this 2 drops down. I then multiply this 2 by that 2, and that's how I get 4. I add these columns, that's how I get 11. 11 times 2 is 22. Add negative 3, and that's how I get 19. And remember, I got this line right here from the coefficients of the numerator. Okay, so once I do the synthetic division, now I have turned the problem into something that I can actually integrate. So now we have this new problem right here. The first 2 terms, again, are pretty easy to integrate. So the integral of 2x is x squared. So that's how I have that in the answer right there. The integral of 11 is 11x. So those are just bump up and divide terms. And then the 19 over x minus 2 fits the log rule, okay, because this was really 19 x minus 2 to the negative 1 power, okay, and so that's the antiderivative of that is going to be 19 natural log of the absolute value of x minus 2. Okay, so that's how I have that in the final answer, and then don't forget the plus c. Okay, here's a similar example. What you have to be careful of here is that the numerator has some missing terms. So again, I can use synthetic division because I'm dividing by x plus 5, and the numerator has a degree higher than the denominator. Okay, so again, I'm going to put the 0 of the denominator in the box here, and then start synthetic dividing. This 0 is here because the numerator is missing an x squared term. Okay, so I drop down my 1, multiply 1 times negative 5. That's how I get the negative 5. Add to 0, so I get negative 5. Negative 5 times negative 5 is positive 25, plus negative 6 is 19. Then I do negative 5 times 19. I think I did that right. I believe that's negative 95. And then add to negative 20 to get my remainder. Okay, so just in case I wasn't clear in the last example, okay, remember that these coefficients began with x cubed, and so when I divide one time, these coefficients now start with x squared. So I'm going to have x squared minus 5x plus 19, and then minus 115 divided by the original denominator, which was x plus 5. So remember, the 115 is your remainder. Okay, so we turn the problem into something much easier. And so these first three terms, I'm just going to integrate like normal using the power rule. Okay, so that's how I got 1/3 x cubed minus 5x squared plus 19x. And then again, similarly to the last problem, this right here is going to fit the log rule because the denominator is bigger degree by 1. So this is going to be 115 x plus 5 to the minus 1 power. And so that's going to be 115 when I take the antiderivative, natural log of the absolute value of x plus 5. Okay, example 5. Well, if you notice, example 5 is not similar to problems 1 through 4. So in example 5, the degree in the numerator is actually smaller than the degree in the denominator. And so because of that, I'm not going to use synthetic or long division on this problem. And so I have to revert back to previous techniques. Okay, so what I probably want to think about here is using a substitution. Okay, so you can see the work typed in there. So I'll just rewrite it down here. If I let u equal to the denominator, that's x cubed plus 6x squared plus 5. Oops. Which means that du is going to equal to 3x squared plus 12x dx. Okay, well, I have a constant multiple of 3x squared plus 12x in the problem. If you notice, I have x squared plus 4x dx, and so I'm just going to divide this equation by 3 so that I have what I need. So this is going to be x squared plus 4x dx. Okay. So here's kind of the work being shown right here in this line. Okay, and so you can see exactly what I did. I just rewrote this integral. Remember that this part right here is going to be replaced by the 1/3 du part. Okay, and then this part right here is going to correspond to the over u part that's in the denominator there. And then the antiderivative of that, of course, is natural log of absolute value of u. Okay, so be careful because not every problem necessarily is long or synthetic division when it is a fraction. Sometimes it'll also be possible. Okay, Roman numeral 2, we want to talk about inverse trig derivatives. So here are the rules for inverse trig integrals that you should be concerned with. Really, you only care about the arc sine and the arc tangent rules, and these should definitely be memorized. Without memorizing them, there's really no way for you to be able to work these problems. Okay, so we're going to work some basic examples that utilize these formulas first. So example 1 is the integral of 1 over the square root of 4 minus x squared. Okay, well, I should recognize that this is not a u substitution problem, because if I were to choose a u, really the only choice is 4 minus x squared, which would make du negative 2x dx. And I don't have the variable part of du in the original problem. So this is not going to work. I'm not going to be able to use a u substitution on this problem, and so I have to think about some other kind of method. Okay, well, in this case, it kind of looks similar to the arc sine rule. Okay, and so notice that this right here is your a squared, and this right here is your u squared. And so if a squared is equal to 4, that means that a will equal to 2. And if u squared is equal to x squared, that means that u will equal to x. Okay, and if u is equal to x, then notice that du is equal to dx, and that's exactly what we have in the problem right there. Okay, so this is an arc sine problem with a equals to and u equals to x, and so the rule for that is arc sine of u divided by a plus c. So that's how I got the answer down here. Okay, just so you know, both notations are technically correct, and you could see either one show up on the AP exam. So you need to know that the arc sine notation and the sine to the minus 1 power, those two things mean the same thing. Okay, here's example 2. Again, this is not a substitution problem, really for the same reason as example 1, because if I take u to be the denominator, then du is going to equal to 18x squared dx, and we don't have the variable part, the x squared dx, in the problem. Okay, so we're not going to be able to use a substitution here, and so this is not going to work. Okay, so I try something different, and I remember my rule about arctangent, and remember that this 2 represents a squared, and this 9x squared represents my u squared. Okay. So if a squared is equal to 2, that means that a is going to equal the square root of 2. And if u squared is 9x squared, then if I take the square root of that, then u is going to equal to 3x. Now, one important part about u being equal to 3x is we don't have du currently in the problem. So remember that du, or u prime is how I wrote it here, u prime is equal to 3 is missing from the problem. Okay, so we're going to need a 1/3 in our answer to account for this. And this is a subtle thing, but it's definitely important to getting the correct final answer. Okay, so I rewrite the problem down here. The 1/3 that I was talking about is here. I went ahead and put in the 3 here. And notice that if those weren't there, they would cancel out and give me what I started with. Okay, so down here I have the square root of 2 squared plus 3x squared. So this tells me that this is a, and this is u. And so I use my formula, which says 1 over a arctangent of u over a plus c. And I just plug into that formula to get the final answer here. Okay, example 3 is similar, so we have actually have too many dx's there, so let's actually cross that one out. We don't need that one. This looks like the inverse tangent rule with a equals to 4, because remember this is a squared, and u is equal to 5x, because remember this part would be our u squared. Okay, again, we're missing the 5 from the problem. So we're missing u prime is equal to 5, and so we have to account for that when we work the problem by putting this 1/5 in there so that we get the correct answer. Okay, so our answer is going to be 1/5. That comes from needing that in the problem because the 5 was not there originally. 1/5 times 1 over u, or 1 over a, I'm sorry, and a was 2, arctangent of u, which was 5x, divided by a, which was 2, plus c. So the 1/5 and the 1/2 multiply together to give me the 1/10 that I had in the final answer. Okay, this is a definite integral, so the answer is going to be a number, and we're going to have to use the fundamental theorem of calculus to figure out what that is. So this is not a substitution problem, again, for the same reason as examples 1 through 3. So instead, I recognize that it's the inverse sine rule because I see the square root of a squared minus u squared. So the 1 represents a squared, and the 9x squared represents my u squared. Okay, so in this case, u is going to equal to 3x, and du is equal to 3 dx, which in this case, unlike the last two examples, we actually have 3 dx in the problem. So we're not going to have to worry about putting a fractional constant in the front of our integral this time. Okay, so this is going to be, I'm down here now, this problem is the original problem. The antiderivative of this is going to be arc sine of u, and so u is equal to 3x, and I evaluate that from 1/6 to 0. Okay, so remember by the fundamental theorem of calculus, I plug in the upper bound first, so that's how I get arc sine of 3 times 1/6, which of course is arc sine of 1/2, okay, which is right here. And then arc sine of 3 times 0, of course, is just arc sine of 0. Now remember, arc sine of 1/2 is asking you which angle has a sine value of 1/2, so I clearly know that that is pi/6, or at least I should. And then I know that arc sine of 0 just means the angle whose sine is 0. And so what you don't see here is subtracting 0, since arc sine of 0 is 0. Okay, so the final answer is just pi/6. Okay, completing the square is also another technique that we typically use to solve more challenging integrals in calculus. Completing the square was a technique that you learned in Algebra 2 when you were trying to solve quadratics. Okay, so remember that when we complete the square, we're taking half of the coefficient in front of x, or sometimes called b, we're squaring it and adding it to the problem, and then we factor. Okay, so in order to not change the problem, when I add that b/2 squared, I need to subtract that term as well so that it seems like I'm adding 0. So I start with ax squared plus bx plus c, which is just your typical form of a quadratic. I take half of b, so that would be b/2, and I square it, and I add that to the problem. Then to make sure that I don't change the problem, I subtract the same term, and then my plus c is there from before. And then what I have is I have x squared plus bx plus b/2 squared, and this will factor into x plus b/2 squared. And the reason for that is because if you were to multiply that back out, then you would have x plus b/2 times x plus b/2, which would give you x times x, which is x squared. Then you would have b/2x plus b/2x, and then multiplied by b/2 times b/2, which is your b/2 squared. And then if you collect the like terms, b/2 plus b/2 is just b, so x squared plus bx plus b/2 squared. So hopefully that didn't confuse you. All I'm trying to show you is that this factorization is what you're going to use when you complete the square. So hopefully all of that kind of rings a bell from Algebra 2. Okay, so here's example 1 where we have to use completing the square. And the way that I know that is because there's only a quadratic in the denominator, and so that really kind of tells me that I'm going to have to use completing the square. Okay, so here's my b term. Half of that term is going to be 2, and when I square it, I get 4. So here's the 4 that really represents my b divided by 2. And then because I added 4 to the problem, I need to also subtract 4 to keep the problem the same. Okay, so then I have the x squared minus 4x plus 4. That's going to factor to x minus 2 squared. And then I combine the minus 4 and the plus 7 to give me plus 3. Okay, so I rewrite the problem now after I complete the square. Now my problem looks like this, and this looks like the arctangent rule. Okay, so where a squared is going to equal to 3, and u squared is going to equal to x minus 2. Okay, so that's going to mean that a is equal to the square root of 3, u is going to equal to x minus 2, which means that du is going to equal to dx, and you see dx is already in the problem right there. Okay, so the answer, remember the rule for arctangent is 1 over a, so this right here is my a, arctangent of u over a plus c. Okay, and so you see the final answer clearly there. Okay, very similar type of example here. So again, only a quadratic in the denominator. So this needs to be done using completing the square. If I take half of the b term here, that's going to be 3. If I square it, it's going to be 9. So this right here represents my b over 2 squared. If I add 9, I have to also subtract 9. And then if I factor the x squared minus 6x plus 9, that's how I get the x minus 3 squared. Combine the negative 9 and the positive 13, and that's how I get the plus 4 right here. Okay, so I rewrite the problem after completing the square. This again looks like inverse tangent. So this is going to be my a squared, and this is going to be my u squared. And so if a squared is equal to 4, that means that a is equal to 2, and u is going to equal to x minus 3, which means that du is equal to dx. Very similar to last problem, means that we're good to go. Okay, so my final answer, I just used the formula. It's going to be 1 over a, which was 2, arctangent of u over a plus c. Okay, so just writing those a's and those u's there so it's clear where I'm getting those terms and those numbers from. Okay, example 3 is a definite integral, so the answer is going to be a number, of course. And in this case, the x squared term is negative, and so this is going to be a little bit more challenging, only because we're going to have to factor out a negative to kind of make the problem make sense. Okay, so down here I have my completing the square, so 3x minus x squared. Because that negative is in front of the x squared, I'm going to factor out a negative from the problem. And so really what I start off with is negative x squared minus 3x, just changing the signs of both of those and kind of rewriting it in a way that you're used to. Okay, then what I'm going to do is still inside of the brackets here, I'm going to add half of b squared. So that's going to be 3 over 2 squared, and then I have to also subtract so that I don't change the problem. 3 over 2 squared. Okay, so you see that clearly typed. Right there, I'm just rewriting it so that I can kind of explain it a little better. Okay, now this part right here, I'm going to factor. So remember that that factors to x minus 3 halves squared. So that's what I have here. And notice that I still have my minus sign out here in front of the bracket. And then minus 3 halves squared, just kind of carried over from here to here. Okay, and then I distribute my negative. So I'm going to distribute my negative to both terms. So to this one, and then finally over to this one. That's how I get the positive 3 halves squared and then minus x minus 3 halves squared. So this kind of looks a little odd when I typed it. Probably the way that you might write that would be like that. Okay, so now down here on this line, we have the integral from 3 halves to 9 fourths, 1 over square root 3x minus x squared dx. I just rewrote the problem after I completed the square. And this looks a lot like the inverse sine rule, where this is a squared and this is u squared. Okay, so using the fundamental theorem of calculus, just coming down to this line now, this is going to be arc sine of u over a. And when I plug in 9 fourths to x, that's going to give me 9 fourths, I'm just doing this over here, the arithmetic, minus 3 halves divided by 3 halves. Okay, if I get a common denominator up in that numerator, that's going to be 9 fourths minus 6 fourths, which is 3 fourths, and then multiply by the reciprocal of 3 halves, which is going to be 2 thirds. This is being multiplied, which is equal to 6 over 12, which is 1 half. So that's how I got the 1 half right there. And then the fundamental theorem of calculus says to subtract and then plug in the lower bound. So if I plug in the lower bound, 3 halves minus 3 halves is going to be 0. So that's how I got arc sine of 0. And then we did this calculation in an earlier problem. Remember that this right here is equal to pi over 6. And this right here is equal to. Okay, so this example is very similar to the one before, so we complete the square as we did in the previous problem. The first thing that needs to happen, since the x squared term is negative, is we're going to factor out a negative. Okay, so up here I'm going to do that, negative, and then the signs of all these terms are just going to change, so x squared plus 2x minus 1. And then to set up my completing the square, I know that I have to take half of b, which is 2 in this case, and square it. So I'm going to do x squared plus 2x. That's going to be plus 1. Okay, I'm going to go ahead and put that in parentheses because that's the part that I'm going to factor. Now, because I added 1, I have to also subtract 1 so that I'm adding 0. And then there was already a minus 1 in the brackets. So I have to put the other minus 1 over here. Okay, so just kind of cleaning that up, that's going to be negative. Factoring what's in the parentheses is going to give me x plus 1 squared, and then combining the two negative 1s will give me negative 2. And so that's going to equal, if I distribute the negative, 2 minus x plus 1 squared. Okay, so there's the completing the square part. Now we are down here working this problem, and this looks like the arc sine rule, or the inverse sine rule. So remember that this is a squared, this is my u squared, so this is going to be a is equal to the square root of 2, and u is equal to x plus 1. Okay, so the antiderivative is going to be the arc sine of x plus 1 over the square root of 2, which is my u divided by my a. If I plug in 0, the upper bound, using the fundamental theorem of calculus, this is going to be the arc sine of 1 over the square root of 2. Then I subtract, plug in negative 1. That's going to be arc sine of negative 1 plus 1 over the square root of 2, which is just 0. So that's how I got this right here. And so now I'm looking for the arc sine of 1 over the square root of 2, which is just the angle whose sine value is 1 over the square root of 2, or you might be more used to seeing it as square root of 2 over 2. So that, of course, is pi over 4. And then we talked earlier about the arc sine of 0 being 0. So what you don't see there is my subtracting 0 from the final answer. Okay, so that pretty much concludes the lesson. So hopefully this video was helpful for you. This is the challenge problem, so see if you can work this problem by yourself, and if you can answer it correctly with all work shown and without cheating in any way, and then show me the answer and your work, then I'll do something to give you a bonus towards your grade. Good luck, and let me know if you have any questions. I will be back tomorrow to answer any questions in tutoring. See y'all later.